So, what the periodic shielding effect decreases, or sorry, increases going down. Is that right? So the number of rings increase, which means shielding effect increases, or core electrons increase. All right. So Sarah and Owen can't answer. Somebody else tell me, how does shielding effect change as we move across a period?
Shielding doesn't change.
Very good. Shielding doesn't change. It stays the same. Stays the same across a period. What is effective nuclear charge? Somebody tell me. Yes, Harris. Okay. The actual charge that valence electrons feel when considering shielding effect. Is that right? The actual charge that the valence electrons feel. So, supposing this is my valence electron. Are you with me? All right? This is my nucleus. All right? So these are all my core electrons that are on the inside. Is that right? This is also core electrons on the inside. Are you with me? So these core electrons act like shields. Yes or no? When they act like a shield, what do they do to the nuclear force? They dampen it. Yes or no? They decrease it.
Yes.
So the actual force that, if this is the valence electron, what is the actual force or pull it's feeling from the nucleus, taking into account the shielding effect, is known as effective nuclear charge. Do we understand? How does effective nuclear charge change going down a group? It decreases. Very good. Effective nuclear charge decreases because there is an increase in the amount of shielding or core electrons.
Yes.
How does effective nuclear charge change as we go across a period? Those who haven't answered should put up their hands and answer. Yes, Matthew? It increases. Why does it increase? Because the core electrons remain the same, but the nuclear charge increases, or the number of protons increases, increasing the effective nuclear charge. Yes or no? Okay. Can somebody define atomic radius? Someone who has not answered before. What is atomic radius? Nadia.
Radius is half the distance between nuclei and two identical atoms.
Okay, so 1/2 the distance between two neighboring nuclei. Does that make sense? So you put two together, two atoms together, and 1/2 the distance between their nucleus is called the radius. What is the trend for atomic radius as you go down a group? Someone who has not answered before. What is the trend in atomic radius as you go down a group? Yes, Charlie? It increases. Very good. So atomic radius increases as you go down a group. What is the trend in atomic radius as you go across a period? Zaina? It decreases when we go across a period. Now, we're going to skip reactivity and we are going to come to ionization energy. What is ionization energy? Someone who's not answered before. What is ionization energy? Tanaya? The energy required to remove an electron from a gaseous atom. Now, what is the trend in ionization energy as we go down a groove? What happens to ionization energy or the energy required? So the nucleus is pulling this electron. Is that right? How much energy do I need to pull this electron away from the nucleus? How does it change going down a groove? It decreases. It decreases. Because the effective nuclear charge is decreasing, the amount of energy that I need to pull out is also decreasing. What is the trend going across a period? What is the trend going across a period? Someone who has not answered before. Yes, Kira. No. So what happens to effective nuclear charge as we go across a period? What increases? Therefore, ionization energy will also increase because we are fighting a greater force on the other side. Does that make sense? We haven't. And we are just learning it. It's a very simple thing. The energy required to pull an electron out. Okay? But Owen, I think I said try read trends. And I posted a video, a Khan Academy video also on Blackboard. Did anybody check that out?
Yeah.
If you have, then you should be able to understand it as I'm talking. All right. So what is electronegativity? Somebody who hasn't answered before. What is electronegativity? There are kids who haven't answered, and I know who they are. Saraya hasn't answered a question. Vivian hasn't answered a question. Asta hasn't. Riti hasn't. Devika hasn't. Abdul hasn't. Aiden hasn't. Dylan hasn't. One of these kids can tell me what is ionization energy. All you have to do is flip the page. All you have to do is flip the page. What is ionization energy? Oh wait, electronegativity, not ionization energy, right? What is electronegativity? Somebody wants to try who hasn't done it before? I'm waiting. This is an honors class. So you should be able to read and tell me what that means. I'm waiting. Huh? It doesn't have a definition? What does it have? Oh, it just says electronegativity and it doesn't tell you what it is. Okay? I will tell you what it is. Electronegativity is the relative ability of an atom to attract a pair of electrons in a bond. In a bond. So what does that mean? What is the difference between ionization energy and electronegativity? All right? So let's say let's say this is a bigger atom. Are you with me? This is a really big atom here, and this is the really small atom here. Are you with me? And there is a pair of electrons between them. Okay? So when two atoms come together and bond with each other, there is a tug of war for this electron cloud, or the distribution of the electron cloud. All right? The electron cloud is there around this, is there around this. But when they bond, it redistributes. Around which will you have a greater electron cloud? Yes, Abdul?
I'm not 100% sure, but it's like the hydrogen and oxygen. We do this here for water.
Uh-huh.
It creates polarity.
Uh-huh.
And oxygen usually has the electron more.
That is correct. That is correct. Because oxygen is more electronegative. Excellent. You know what? This is Abdul. This is the first year I have heard that a student say, we actually learned this in 9th grade. All right? If I say, have you learned this in 9th grade? They'll be like, oh no, the teacher never mentioned it. You never learned any of it. If I go ask the teacher, it's like, I taught them that. And I know that year after year, kids will say, oh, we never did it. Yes, you did. And I'm happy to hear that a kid remembers that. All right? So anyway, this electron cloud, are you listening? This electron cloud will distribute more around the smaller atom. And the logic is this. It's closer to the nucleus. Is that right? So the pull on the electron cloud will be more. Does that make sense? So in a bonded situation, which will have a greater control of the electron cloud. Now we still learn sometimes electron as a particle. Is that right? We keep switching back and forth. And so we say attract a pair of electrons in a bond. So now tell me, what is the trend of electronegativity as you go down a groove? Somebody who's not answered. What is the trend in electronegativity? Yes, Devika. It decreases. That's right. The effective nuclear charge decreases. So even in a bonded situation, the nucleus will not be able to pull it closer towards itself. Is that right? What is the trend going across a period? Yes, Aska. It increases. That is correct. Electronegativity increases. Now, that brings us to the discussion of why do we learn periodic trends? What is the point? Okay? So let's come to, well, I don't know if you have space in this page. So my last class complaint, there was like, there's no space. On the back of your warm-up, do you have an atomic radius warm-up? A periodic trends warm-up? The back is blank. So what I want you to do is draw a periodic table. On the back of the warm-up. These are notes and you should know this. That's all I care about. All right? Now, what is the left of the periodic table called? What do we have? The metals. Is that right? These are the metals and these are the non-metals. Now, I say metals are losers.
I agree.
Metals are losers. What do they lose? They lose an electron. All right? If they lose an electron, what do they become? What do they become?
Losers.
A cation. They become a? What do they become? They become pluses. They become plus. They become cations. And it's the opposite for the non-metals. So non-metals will gain electrons and they will become anions. Is that right? Metals become cations, non-metals become anions. Now last class, you did a lab. You did a little activity otherwise, not a lab. Which three metals did you compare? Does anybody remember which three metals? Okay, quite a few hands up. Yes, Riti? Magnesium, aluminum, and calcium. If you look at these three metals, magnesium and calcium belong in the same group. Magnesium and aluminum belong in the same period. Yes or no? Now, out of the three, which is the most reactive metal? Calcium. Is that right? And the least reactive was aluminum. Why? Why is calcium the most reactive metal? So if you're talking about reactivity of metals, what will you say is the reactivity of the metals? You will say reactivity of the metals is their ability to lose electrons. So they can lose an electron easily, then they are more reactive. If they can't lose it, then they are less reactive. Yes, Abjot?
So calcium can lose 2 electrons while aluminum 3 and what about magnesium?
Well, calcium and magnesium are both 2. It doesn't have anything to do with the number of electrons. It generally has to do with how easily can it lose an electron. So let's compare the size of magnesium versus calcium. Which is bigger?
Calcium.
Calcium. Which has lesser ionization energy? From which is it easier to remove an electron?
Calcium.
Calcium. Therefore, calcium is more reactive. If we had just done the lab and we hadn't learned trends, why? Why is it reactive? I don't know. It's reactive. Now you kids can say, well, isn't calcium bigger in size? Isn't it easier to remove the electron? It's going to be more reactive. Supposing I pitch 2 new metals to you. I'm comparing sodium and cesium. Which do you expect to be more reactive? Cesium. You know the reason why. Does it make sense? You know now to reason it out. Similarly, if you compare magnesium and aluminum, which is smaller in size? Wow.
I said aluminum. I think your earrings are.
Okay. So, what happens to size as we go across? It becomes smaller. Ooh, we are having trouble remembering these things. It becomes smaller as we move across the period. Aluminum is smaller than magnesium. So is it going to have a higher or a lower ionization energy? Higher. We are getting all mixed up. Because it requires a lot of energy, the surrounding water, you put aluminum in water. Yes or no?
Yes.
Water can very easily remove an electron from calcium. And calcium becomes reactive. Can water remove it from aluminum? No. Water doesn't have that much energy. So aluminum will be non-reactive. That's why we like using aluminum when we cook stuff. Because it's non-reactive. Duh. It's a no-brainer. Right?
Iron.
Alright. So what about non-metals? Non-metals is the ability to gain electrons. What happens to reactivity of metals as we go down a groove? It increases. What happens to reactivity as we go across? It decreases. The opposite is true for non-metals. As we go down, it It decreases, and as we go across, it increases. So kids are having a lot of trouble trying to rationalize and remember trends. Is that right? So we're going to go back to the warm-up, back of the warm-up, and we're going to draw.
Right.
Abdul, I'll take your question in a minute. All right? So on a test, on a quiz, how are we going to remember the pattern or the trend? All right? What is it, Owen?
It's like, it'll help you, like, when you go home and you forget it. And you can
Even on
also-
a test or a quiz. Okay. Draw a snowman. What are we drawing? What does a snowman indicate? Which trend? Atomic? Radius and kind of shielding also, right? So it indicates atomic radius. What happens to radius as we go down a groove? It gets bigger, it increases, however you want to say that. Increases or gets bigger. Is that right? So if you go across a periodic table, are you with me?
Yes.
How many circles have I drawn here? 3. How many circles will I continue to draw? 3, but what happens to those circles? They get tighter and tighter. Is that right? So what is the trend in atomic radius as you go across a period? It decreases or becomes smaller. All right? The two other trends, ionization energy and electronegativity. I'm going to abbreviate ionization energy as IE and electronegativity as EN. They are both the opposite of radius. What should you remember? Snowman, and say the remaining is opposite. So then, if the radius gets bigger, I need lesser energy or there will be a lesser pull. Bigger the radius, lesser is the energy. So ionization energy decreases, or as you go down, we need lesser energy to remove an electron. Or a bigger atom will not draw the electron pair towards itself. Does that make sense?
Wait, I'm sorry, what's the red one again?
Red one is ionization energy and electronegativity. I abbreviated that. Again, like I said, it's the opposite. If the radius is decreasing, what will happen to ionization energy? It will increase. You need more and more energy to remove from a smaller atom. Or in a bonded situation, the smaller atom will pull the electron pair towards itself. You remember that? Whereas shielding increases, shielding remains constant. Is that right? And for metals and non-metals reactivity, you should of course remember that metals have the reactivity increases and decreases like the radius. Is that right? Whereas for non-metals, it's the opposite. Are we good? This table is a one-shot place where you can learn all the